Hello, everyone, distinguished guests and fellow technology enthusiasts. I'm going to talk about one of the most groundbreaking advancements in the field of machine learning. Federated machine learning is an approach that allows multiple parties to collaboratively train a machine learning model without sharing their private data. It addresses the challenge of data privacy and security while still benefiting from large and diverse data sets from different sources. So let's get started. So I've got just 2 points to talk about in this video. We'll talk about what federation machine learning is, and we'll talk about different techniques that are used in order to implement federated machine learning. So let's get started. But before we get started, let's talk about traditional way of training machines or performing your machine learning model. So in recent years, we have witnessed an exponential growth in data generation and an increasing need for sophisticated machine learning models to extract valuable insight. Artificial intelligence and machine learning offer the ability to learn from experience and refine models without being specifically programmed. These innovations have become common use in recent years. They have been used in several different fields and various applications. For example, analysis of participants' data from a vehicle fleet in the automotive industry provides insights for customer needs, vehicle activities, and driving environment. New vehicle data analysis strategies include sending compressed sensor data from all the vehicles to a central server and conducting the data analysis operation. The entire data set is available for training the model, and the training process occurs on the centralized server. The data is usually collected from multiple sources, but it is combined and stored in one place before model training takes place. Traditional machine learning models require the data to be centralized in a given location or server. However, this progress has been impeded by legitimate concerns regarding privacy, security, and data ownership. So if we talk about the challenges that comes with the traditional machine learning models are your data privacy. Centralizing the data raises concerns about the privacy as well as the data is stored and accessed in one location. It may involve sensitive information, and there is a risk of unauthorized access or data breaches. Second concern that we see is with the data transfer itself. In some cases, transferring the entire data set to a central server can be time-consuming, resource-intensive, and costly, particularly if the data is large or distributed across various locations. Third challenge that we face is legal compliance. Centralizing data may also raise legal and compliance issues, especially if the data represents individuals or entities from multiple jurisdictions with different data protection regulations. So what's the solution? One of the solutions is to use distributed machine learning model. Distributed machine learning model algorithms are designed to resolve the computational problems of complex algorithms on large-scale dataset. The distributed machine learning algorithms are more efficient and scalable than centralized algorithms. Here, in the distributed machine learning model, the models are trained with same methodology as in centralized machine learning models, except they are trained separately on multiple participants. During the training in a distributed algorithm, the participants independently train their models and send the weight updates to the central server. At the same time, the central server receives updates from the participants and performs averaging for output. After the certain communication rounds, the convergence testing is done on the central cloud server. Now enters the federated machine learning model. Your federated machine learning model is a revolutionary approach that combines the power of collaborative learning and data policy, ushering in a new era of machine learning applications. Federated machine learning, in essence, is a system that enables multiple entities to collaboratively train a machine learning model while keeping their data decentralized and secure. Instead of sending all the data to a centralized server, the data remains on the local devices or server, and only the model parameters are exchanged during the learning process. The only difference between distributed machine learning and federated learning is that in the federated learning, each participant initializes the training independently, as there is no other participant in the network. So each of these participants in the network are independent of each other. In federated learning, the training is conducted collaboratively and independently on individual participants. In particular, local epochs are declared in the learning parameters. Each participant trains the data by running the local epoch. After specific amounts of epochs, the local update is computed and other participants send the updates to the cloud server. Cloud server receives the updates from each participant, average them, aggregate the next global model. Based on this global model, the participants execute the training process for the next communication round. Process kept repeating until the desired convergence level is achieved or the given communication rounds are complete. The federated machine learning model overcomes the limitations by distributing the model training process across multiple devices or edge devices while keeping the data locally. In this approach, data remains on the local devices and is not shared with the central server or other participants, ensuring data privacy and confidentiality. Data ownership. Users or entities retain ownership of the data and have control over its usage, reducing concerns about relinquishing control of sensitive information. Data storage and transfer. The need to transfer large amounts of data to a centralized location is minimized or eliminated. Only model updates or gradients are shared between the devices and the central server, reducing the burden of data transfer. Legal compliance. Federated learning can be designed in a privacy-preserving manner that aligns with the data protection regulations and complies with legal requirements without the need for centralized data storage. Now let's go and see some of the advantages that federated machine learning model offers to us. First is data privacy. The concept of federated machine learning addresses the challenges of data privacy and security by minimizing data exposure. As the data remains on the local devices, the risk of data breaches or unauthorized access is significantly reduced. Federated learning eliminates the need for data aggregation, thereby reducing the vulnerabilities associated with centralized data repositories. The second advantage is the processing of real-world data. In this case, federated machine learning leverages its ability to. Another significant advantage of federated machine learning is its ability to leverage distributed data sources. In conventional machine learning, a central server typically trains models on large homogeneous datasets. However, in federated learning, each participating entity retains the ownership of their data, enabling a more diverse and representative training sample. This decentralized approach enhances the robustness and generalizability of the trained models, enabling them to perform better in real-world scenarios. Federated machine learning promotes scalability and efficiency. By distributing the computational load across multiple devices, federated learning enables parallel processing, leading to faster convergence and reduced training time. This aspect is particularly valuable when dealing with large-scale datasets, where centralization often becomes a bottleneck. Federated machine learning is highly relevant in scenarios where data cannot be easily shared due to regulatory constraints, contractual agreements, or intellectual property concerns. Industries such as healthcare, finance, and telecommunications stand to benefit immensely from federated learning, as it allows different entities like banks, hospitals to collaborate without compromising sensitive information while still extracting meaningful insights. Okay, those features are great, But how does machine learning is able to perform all these? So in the next few minutes, we'll talk about different techniques which are used by federated machine learning models to achieve what we have discussed so far. There are several techniques used. Secure aggregation technique ensures that the model updates sent by the participants are combined without revealing individual contribution, thus preserving data privacy. It allows for the aggregation of locally trained models or gradients without exposing any sensitive information or raw data to the centralized server. The secure aggregation process typically involves the steps like local model training, where each device or client trains a local model using its own data. This can be done using various machine learning algorithms and techniques. Step 2 is encryption. After training the local model, each device encrypts its model parameters or gradients using encryption techniques like homomorphic or secure multi-party computation. This ensures that the model updates cannot be directly observed or used to reconstruct the original data. Third process is aggregation. The encrypted model updates are then sent to the central server for aggregation. The server can perform operations on the encrypted data without decrypting it, allowing the aggregation of the model updates without exposing the raw data or model parameters. Fourth step and the last step here is decryption. Once the aggregation is complete, the central servers can decrypt the aggregated model updates using secret keys or decryption algorithms. This allows the server to obtain the final aggregated model without ever accessing the raw data or individual model updates. Secure aggregation provides several benefits in federated learning, such as privacy protection. Privacy protection, the encryption of the model updates ensures that the individual data or model information is not directly exposed to the central server. This protects the privacy of the users and their sensitive data. Security against attacks. By encrypting the model updates, secure aggregation protects against the attack that aim to extract sensitive information or manipulate the learning process. Data confidentiality. The encryption techniques used in secure aggregation ensures that the central server cannot access the raw data or model parameters, maintaining the confidentiality of the information. Compliance with the regulations. Each aggregation enables federated learning to comply with data protection regulations such as the General Data Protection Regulation (GDPR) by minimizing the exposure of personal data to third parties. However, secure aggregation also has some limitations. The encryption and decryption process can introduce additional computational overhead and communication cost, which can impact the overall efficiency and scalability of the federated learning system. Therefore, it is important to carefully choose encryption algorithms and optimize the secure agreement techniques to strike a balance between privacy and computational efficiency. Second technique that we all generally use is called differential privacy. Now, in this technique, there's a noise which gets added to the model being built by the local servers. By adding noise to the model updates, differential privacy techniques aim to prevent the leakage of sensitive information about an individual data point. This noise makes it difficult for an attacker to determine whether a specific user's data has been used in the training process or to extract sensitive information from the model. The level of noise added is carefully calibrated to balance privacy and utility. It ensures that the individual contributions of each user are hidden while still allowing the model to learn from the combined knowledge of all users. The differential privacy technique is applied to the local model updates performed by each user device. Instead of sending the raw data updates to the central server, each user device first applies a random noise to the update, and this noise is generated using a privacy amplification factor, which determines the overall strength of the privacy protection. The privacy amplification factor is a parameter that determines the amount of noise added to the local model updates. A higher value of this parameter leads to stronger privacy guarantees but may also reduce the utility of the model. A lower value, on the other hand, may improve utility but could compromise privacy. To ensure that the privacy is maintained, a trusted third party typically generates the privacy amplification factor. The third party is responsible for calibrating the role added to the local model updates based on a predefined privacy budget. The budget determines how much privacy protection is provided to each user's data. The aggregated updates are combined using secure multi-party computation techniques, which allow the server to perform the necessary calculations without knowing the individual contribution. By applying differential privacy to federated learning, user privacy is protected while still allowing the central server to learn from the collective knowledge of all the users. This technique provides a balance between privacy and utility, allowing users to participate in the training process without compromising their sensitive data. The third technique that I can talk about is called homomorphic encryption. Homomorphic encryption is a cryptographic technique that allows computations to be performed on encrypted data without decrypting it. This means that data can remain protected and private throughout the computation process. When combined, homomorphic encryption and federated learning can provide a powerful privacy preserving mechanism for training machine learning models on sensitive data such as patient data. How does it work? The step one is data encryption. Each decentralized device, such as smartphone or IoT device, encrypts its data using a homomorphic encryption scheme. This ensures that the data remains confidential and cannot be accessed by the central server or any other party without the decryption key. Then comes model training. The central server initializes a machine learning model and sends it to the decentralized devices. The devices use the model to perform local computations on their encrypted data. These computations include operations like addition and multiplication, which are possible with homomorphic encryption. After performing the local computation, the decentralized devices send the encrypted results back to the central server. The server then aggregates these encrypted results to obtain a combined result without decrypting any data. And the last step here is decryption and model update. The central server decrypts the aggregated result using the decryption key. It then uses this result to update the machine learning model. Updated model is then sent back to the decentralized devices for subsequent iteration for the training process. The key advantages of using homomorphic encryption in federated machine learning are the privacy preserving. Since the data remains encrypted throughout the process, the central server does not have access to the raw data. This helps protect sensitive information and ensures that user privacy is maintained. Now we'll talk about security. Homomorphic encryption provides a strong level of security by ensuring that the data remains confidential and protected from unauthorized access. Even if the encrypted data is intercepted, it could be of no use without the decryption key. Third step is called decentralization. Federated learning allows training models on decentralized devices, and use of homomorphic encryption extends the decentralized nature to the encryption process as well. This promotes data ownership and control by the device owners while still enabling collaborative model training. However, there are some challenges and limitations before you consider homomorphic encryption. Efficiency. Homomorphic encryption is computationally expensive and can introduce significant overhead in terms of time and resources required for encryption, decryption, and computation. Limited operations. While homomorphic encryption supports basic operations such as addition and subtraction and multiplication and division, more complex operations required for machine learning tasks may not be fully supported. Implementation and maintaining a homomorphic encryption scheme requires considerable expertise in cryptography and adds complexity to overall federated machine learning model. In summary, homomorphic encryption in federated learning offers a promised solution for privacy-preserving machine learning on sensitive data. It can help protect user privacy and enable collaborative training without the need to share raw data. However, it comes with some challenges and limitations that need to be carefully addressed for practical implementation. With that, we come to end of this presentation on federated machine learning. Hope I have been able to give you some idea about this new technique. So we'll end this discussion here and I'll see you in next video.